Welcome back, students, to the second lecture of Turing machine. So before starting with today's class, I'll just quickly recapitulate whatever we had learned in our last class. So we had actually formally defined the Turing machine. We have seen the structural components of a Turing machine, and we had also seen an example of a to the power and b to the power n, that is how to construct a Turing machine, rather the state transition diagram of a Turing machine that accepts all the languages of the type a to the power and b to the power. And additionally, I had also told you that Turing machine is the most powerful of all the four machines, and it has a capability of not only acting as an acceptor, but at the same time it can act as a generator, as well as it can act as a transducer. And what does a transducer mean? A machine that is capable of performing mathematical calculation is nothing but a transducer. So today we will see some more examples of Turing machine, and today I'll be focusing on transducer, that is how a Turing machine acts as or performs as a transducer. Okay, so the first example that we'll work with today is ones complement. That is, we will design a Turing machine to find the ones complement of a given binary number. So we are quite familiar with ones complement, right? So I've given an example over here. Our binary number is 0011, and obviously you all know the ones complement. The output of this will be 1100. That is, zeros are flipped as 1 and ones are flipped as zeros. Right. So now, when we are asked to design a Turing machine that can perform the functionality of one's complement, we'll just see how does this work. So this is the tape structure. Okay. This is more or less the tape structure. As you can see, we have blank symbols at both the ends, and we have our input language, that is input text 0011. And our read write head is at, let me take this one. Yeah. So read write head, it is at this point, this 0, at the initial point of time. So what we're supposed to do is we'll start traversing the tape, the Turing machine tape, and we'll change the 0 to 1. We're going to change the 0 to 1. As we move towards the right, our input output or read write head will be at this next point, right? And we are going to change this 0 again to 1. Again, we will be moving to the right. Okay, and now our input output head is at 1. In the next step, we are again going to change this 1 to 0. Again, we are going to move right, and the input output head will be at 1, right? In the next step, we will finally change this 1 to 0. Okay, at the last step, what we are doing, see, it's actually not a rule or not a mandate. It's a courtesy that will bring back the read write head to the initial point where we had started. Okay, so this is the basic logic, and it's quite easy. Okay, so now we'll just directly go to the construction of the state transition diagram. And one more thing, students, if you look at this carefully, you can see that we do not have a need of a final state over here, as it is not accepting anything, right? It is actually generating the ones complement of a given number. It is performing a particular mathematical calculation, but it is not accepting anything. So we do not have a final state over here. We just need the Turing machine to halt at a particular point, right? So fine, we will just directly go to the state transition diagram. So here we have our state transition diagram. So let's see. So Q0 is our initial state, and as we had seen, whenever we get a 0, we are changing it to 1 and moving to the right. Again, if you're getting a 1, we are changing it to 0 and moving to the right. Fine, we are complementing it. Now, in the next step, what we are doing, whenever we get a blank, that is when we are at our extreme right and we encounter a blank symbol, we keep the blank intact and we move the read write head to the left. Fine, we are reaching this state, Q1. Once we are at Q1, now what we will do, we have already like done the ones complement. We have flipped zeros to 1 and 1 to zeros. We are done with that, right? So now we will just keep the zeros intact and move, like keep moving towards the left, and we'll keep the ones intact and we'll keep moving towards the left until and unless we reach the blank symbol. This is the blank symbol at my leftmost end, mind it. This was the blank symbol at my rightmost end. See, this was the blank symbol at my rightmost end. This is the blank symbol at my leftmost end. So once I have reached the blank symbol at my leftmost end, I'll keep it as blank, I'll keep it intact and move towards my right. Why I am doing this entire thing? See, this entire thing is done just to bring back my read write head back to the initial point that I have started. Okay, so we are finally reaching the initial state. We are finally reaching actually this point. If we see this structure, so finally we are reaching at this point, or this point, sorry, not this point. We are reaching this point. That is the first point that we had started with. Okay, so this is how we are calculating the ones complement. Okay, this, yeah. So this is pretty easy and pretty straightforward, right? Calculation of one's complement. Okay, now this you have to do it yourself. I'll just give you the hint, or I'll just give you the concept how to do it. That is calculation of 2's complement. Same, you have to construct a Turing machine that will give you the 2's complement of a given number. So see, I have just explained to you the concept. So this is my given number, 001100. This is my given input. So you all know what is the process of getting the 2's complement. You have to first flip the zeros to ones and one to zeros, that is get the ones complement, and then you have to add a 1 with this number. So the final 2's complement is 110100, right? Agreed? Now see, this follows a particular trend. If you look at this final output, see, so this is our final output, right? And this was my input. So if you see, starting from the right hand side, whenever we get a zero, whenever we are getting the zeros are kept intact. See, we had a 00 in the output, we have a 00 at the output as well. So the zeros are kept intact. Next, whenever we experience the first one, this first one is kept intact, no changes there. After that, whatever we are getting, we are going to change that in the ones complement form. That is, we are going to flip the ones to zeros and zeros to ones, as you can see. So this is a very simple procedure. Starting from the right, keep the zeros intact. Once you experience the first one, keep that one intact. And after that, flip the zeros to ones and ones to zeros. I have tried to write it down in simple text. So see, as you can see over here, I have just jotted out the points. As we are traversing from right towards left, keep the number of zeros intact. Whenever we get the first one, keep it intact, and the remaining part should be changed to its ones complement. So see, this is quite easy. You have to construct the Turing machine yourself following this concept. Okay. So I hope you are going to be able to do this yourself. So in our next subsection, we'll be seeing one more example. So thank you. Okay, students, so welcome to the second part of this lecture. So in the previous part, we have seen that how to use a Turing machine for finding the ones complement as well as two's complement for a binary number. So in this part, we are actually going to see that how to add two numbers using a Turing machine. So first of all, before going into the detailed procedure, we'll see that how to represent the input numbers. So here we are going to follow a unary number system. As you can see, we have two inputs, 3 and 4. So for 3, we are going to take 3 ones, and for 4, we are going to take 4 ones, right? So now, since we know that how our input will look like, or we are going to take the input in which form, we'll see the tape structure, the initial tape structure. So as you can see, we have blank symbols at both the ends, and we have two inputs, suppose we are going to add 3 and 4. So we have 3 ones for a 3 and 4 ones for a 4, which is separated by a 0. So the inputs are 0 separated in the Turing machine. Fine. Now coming to the approach, what should be the approach? So the approach is quite simple over here. Simply what we have to do, we'll start at this first one, right? This first one will start, and then moving towards the right, Once we get this 0, we'll change this 0 to a 1. We're simply going to change the 0 to a 1. Once we change the 0 to a 1, see in this entire tape, we are left with 1, 2, 3, 4, 5, 6, 7, 8. 8 ones, okay. But 4 plus 3 gives us 7 ones, right? So what we will do is, once we have traversed the entire tape and we have reached at this particular end, there is a blank symbol at the rightmost end, we are going to move the read-write head towards the left, and the first one that we encounter, we are going to change that one to a blank symbol. Fine. Once we do this, see, we are left with 1, 2, 3, 4, 5, 6, 7 ones, and that is the result we actually need. That is 4 plus 3 gives us a 7. So this is a simple approach that will help us to calculate the sum of two numbers or add two numbers. Okay. So now we'll just quickly go to the transition diagram of this particular problem. So as we can see, we are starting at Q0, and on getting a 1, we keep the 1 intact. We move towards the right. We have already seen that. And once we get a 0, we are going to change the 0 to 1, and we are continuing moving to the right. And we change the state, we are coming at Q1. At Q1 again, we are getting a 1. We keep the 1 intact, we move to right. We get a blank, we keep the blank intact, but we move to the left. That is, we flip the read-write head in the left direction. And then the first one that we are getting, this one, we will change that one to a B, that is this one. So we get a 1, we change this to blank, and we keep on moving left. On moving to the left, we will encounter many ones. We keep those 1 intact and keep on moving to the left. And finally, once we reach this leftmost B, we keep the B intact and turn the read-write head to the right direction so that we can reach our initial starting point. That I had said, it's a courtesy, it's not a mandate, but we try to come back to the initial point where we have started. This is a simple procedure by which you can add two numbers. Next, we will see a similar kind of problem. There is a comparator. So you all are quite familiar with a comparator circuit, I guess. You all have done it in digital logic in your third sem. So a comparator circuit actually gives us three outputs. There is either the two numbers that we're comparing are equal to each other, or the first number is smaller than the second number, or the first number is larger than the second number, right? So these three kinds of possibilities can be there. So here again, we will be taking the inputs in unary number system. See, the two inputs are 3 and 4, and for 3 we have taken 3 ones, and for 4 we have taken 4 ones, which is separated by 0, same as we had done in the previous question. Now see, we are actually going to compare the ones, this one with this one, that is the first one with the first one that we get after 0, the second one with the second one that we get after 0, and this third one with the third one that we get after 0. After doing this comparison, we'll see that one left at the right hand side is left out, and since this is left out, we can conclude that this the second number is actually larger or higher than that of the first number. Okay, so if I try to draw the process, not the transition diagram actually, but the tape structure. So this is my tape structure, initial tape structure. I start from this one, I change this one to X, and I keep on moving towards my right. The first one that I encounter after 0, I'll change that to X. So I am basically comparing this one with this one, right? Okay. Again, we are flipping the read-write head to left and moving towards this direction. Okay. Once we get a X, we will traverse the right of the tape, and we'll change the first one to X again. We'll keep on moving to the right. Once we get an X, the next one will change to X again. So we are actually comparing this with this one. Again, we'll keep moving to the left, and on getting x, we'll again flip the direction, and if we get a 1, we'll change this 1 to x. And again, we'll move to right, and once we get an x, we'll change the next one to x again. So we're comparing this one with this one. So after doing this entire process, as you can see, all the ones in the left hand side of the 0 are exhausted, already exhausted. But we are left with one, this is one with in the right hand side of 0, which concludes that the second number, or the number at the right hand side of 0, is higher than that or larger than that of the first number. So this is a simple procedure. I'll suggest you to draw the entire transition diagram so that the thing is much more clear to you. And after that, if there is any confusion, you all can tell me, and always there to help you out with the solution, the transition. So thank you.